All right, just the schedule here. We're on week 3. And tomorrow we're doing experiment 3, Charles Law, just gases. That experiment, safety goggles are optional. Probably should wear closed-toe shoes, open sandals. We have like broken glass sometimes, or you might spill hot liquids on your feet. And so, shoes, you want something like closed-toe shoes. Safety goggles, you can either wear them here or wait until later in the semester if you don't have them. We're just working with water and air in this one, but hot water too, boiling water. So there's that hazard. Next week we have exam 1 on Tuesday. Exam 1 is going to cover, looks like chapters 1 through 4 and some nomenclature. The nomenclature you're going to have on exam 1 will be like these ions that you have to memorize. Probably not everything, just those ions plus maybe some of the monatomics off the periodic table. Do you know how to get the charges off the periodic table? Pretty much. It's just a matter of getting the pattern. Well, chapter 1, there's not much to chapter 1. Except the scientific method. The scientific method, you'll be tested on that. Yeah. And so, like 2, 3, 4.
Would part of our exam be like knowing the NIMs that you asked us to?
Like the nomenclature, you would, the 10 ions that I asked you to memorize outright, the test would be something like, what is the formula for sulfate? But sulfate, was it one of the 10 that you had to memorize? No, it wasn't one of the 10 because sulfate we can get off a pattern off the periodic table. Just like we get the charges off a pattern off the periodic table. So some things we don't have to memorize. I don't think I'm going to test you off the patterns yet. I'll probably just test you off the ones that you have to straight memorize.
I just feel like we had like a lot of compounds to memorize, so I didn't know which exam we were.
So the question is, you're uncertain about which ones, like if I say what are the 10 ions that you had to memorize, you don't know what the 10 are.
Yeah. Because in like the book there was more than 10.
In the book there's more than 10. That's true. And so it depends. If you're okay with patterns, then there are 10 that you have to memorize. If you're not okay with patterns, then you have to memorize all of them. And so you could either start memorizing all of them, and then maybe 10 out of all those will be on the test, or you can do the patterns to save you some memorization. Whichever way you prefer. There are some people who prefer just to memorize them. They're good at flashcards or whatever else. You know, so what were those? So I wrote them down, but maybe I didn't spell it out so clearly. The 10 that you absolutely have to memorize are highlighted in blue. So we counted them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are the 10 bare minimum that you have to memorize. All the other ones in the book, you either memorize it or you figure it out based on the pattern. So I just asked you about sulfate. I wouldn't have bothered memorizing. This is why sulfate is not highlighted in blue, because I know the pattern. I don't have to memorize it. I could just figure it out based on the pattern. But if you can't figure it out based on the pattern, you need to memorize it. However you get it done, you just need to be able to figure out how to get it done. Does that make sense? The same thing with the charges. I'll tell you, when I did this, I just memorized the charges outright. So for example, iron, I had to memorize the charges on iron. And the charges on iron are 2 + 2 + 3, and I had a bunch of flashcards, but I didn't realize there's a simple pattern. All these are +2 + 3, right? And +1 + 2 etc. Is plus, so we can go on here. So there's a certain pattern: 0, -1. What are these? -2, -3. Plus or minus 4. The reason this is plus or minus 4 is because this is kind of in the center. It could gain 4 or it could lose 4. But gaining 4 and losing 4 is getting more and more difficult. The more electrons you gain and the more electrons you lose, the harder it is. And so to have monatomics at +4 or -4 is a bit odd. But -1 is very common, -2 is common, -3 is fairly common. Getting to -4 is less common. +4 is less common. And so those are usually stabilized by having other atoms of other elements present in there. Whereas these could be standalone monatomics. There are 3 more that we memorized that are in this. All these are variable charge in this region except for zinc, cadmium, and silver. It forms this little elbow here. This little elbow is fixed charge in the sea of variable charge. And so there are other little patterns here and there. Otherwise, you just memorize it. Zinc, cadmium, and silver, what the charges are for those. And so for this quiz is these are them. Does that answer the question about? Okay. So for the test, probably these ones you'll be tested on. I'll give you a little more time to memorize the other ones or figure out the pattern for the other ones, if you don't like patterns. All right, we're gonna move on here. There's something. Like, for example, there are a couple of slides on this electrical character of matter. So sometimes what you do is, what is the significance of this? Did you catch what the significance of this is? This electrical character of matter and in this law here, which we call Coulomb's law. What was the significance of it? And so normally if you have stuff like this, you try to write down like the significance in your own words. Why is it important? Why is Coulomb's law important? A couple of reasons why, but basically quantum mechanics involves these interactions between things. And these interactions are electrical in nature. And so what quantum mechanics is just a fancy version of Coulomb's law. Coulomb's law it's very simple. Positive attracts negative, and then like charges repel. And the force of the attraction or the repulsion depends on the magnitude of the charge and the distance, the size. And so when we do quantum mechanics is a very fancy version of the Coulomb's law because, it depends on the shape of the charge and a bunch of other things. But essentially, this is it. This is chemistry. This is what holds the water molecules together in liquid water. There's this fountain in downtown Los Angeles that shoots out huge drops of water. These drops of water are like this big. And you can watch the drops of water because normally a drop of water is kind of spherical in shape, but these ones are blobs. And the blobs are changing shape. So this giant drop of water gets shot out of the ground, and you can watch it as it's trying to break apart, but it's not able to break apart. It's like this blob that's trying to separate, but what's causing the waters to stick together? What's causing the waters to stick together are electrostatic attractions, Coulombic forces, we call it. And the water molecules are stuck together. You'd like to see the water molecules break free, but they can't break free. It's like taffy; they're stuck in it. And so it's interesting watching these droplets of water shot out, and they don't break apart, and then they hit the ground. And they're huge drops. But it just goes to show you that that's not the only thing. It's like the, did I talk about the cisplatin anti-cancer drug? The chemotherapy agent? It has the right shape, but not only does it have the right shape, but it also has the right electrostatic interactions. It has the right Coulombic forces, so that when it attaches to DNA, it gets stuck in the groove. It's just not hanging there and it can get knocked off easily. It sticks. And what's causing it to stick into the groove of the DNA? It's these electrostatic forces. That's what's causing it to stick in there. And so this electrical character of matter, this Coulombic law, in the morning I asked about this law, but nobody could remember it, but it is very significant. It's very significant for us because it's when we look at interactions between matter, we look at electrical interactions. Those are going to be the strongest. There's going to also be gravitational interactions between these two. There's a law for gravity as well. If you've had physics, you probably have seen this law. It depends on the mass of body A, not the charge, but the mass of body A and the mass of body B and the distance between. And this law of gravitational attraction. You seen that? Maybe you've seen it, maybe you haven't, but it's also an empirical law. What do I mean by empirical? Yeah, derived from observation, experiments, observation. So this is a law that's derived by observations, and the observations are just how strong are these attractions. You measure them. You measure the charge on each of these and the distance and the measure. It's not; these are touching. It's the distance between the center of the balls, and so it depends. You could have a highly charged tiny ball or big ball with low charge. The balls could be touching, but you're looking at, the concentration of the charge. And so the more concentrated the charge, the higher or the stronger the force. And we call that charge density. And so some atoms are big. All the atoms over there are -1. And when I say all the atoms are there as -1, I'm talking about the ions, but what family am I talking about? The -1 family of ions. The halogens, right? All these are -1. And so they all have the same charge, but what's different about them? They all have the same charge, but what's different about them are they all the same size? No. So if you have a -1 on a tiny one, like fluorine's kind of tiny, but iodine's huge, big atom. About how big are atoms? You know about how big atoms are? Are they about like millimeter size? How about micrometer size? What's smaller than micrometer? Nano. Are they nanometer size? No. What's smaller than nano? Pico. Are they picometer size? Yes. So atoms are about picometer size, but not 1 picometer. How many picometers? Meters, but picometers are pretty small. Actually, it's too small, but they're between about 100 to 600 picometers. Nanometers would be like big molecules, protein, that kind of stuff. Nanotechnology, they're looking at big molecules and stuff. But here, they aren't the same size. Like iodine is a lot bigger than fluorine. It has the same charge, so what's different is the charge density. So that's what this term here, the distance, this kind of refers to, the size, the charge density. Anyway, that's the significance of this. So we ended, we're close to with this here. All right, we're moving on to chapter 3 now. So let's take a look here. Chapter 3 deals with measurement and chemical calculations. So there are a whole bunch of learning outcomes. I'm going to skip all of them. Some of this stuff I'm going to just go through very quickly. Like scientific notation. If you need some additional review, there's additional review of scientific notation in the chapter, plus I think there's an appendix math review there. But you're supposed to be able to do scientific notation based on the prereq, which is algebra. So we have coefficient here, the exponential, and the exponent, which is the e. Can you convert from decimal to scientific? Okay, good. And backwards from scientific to decimal. And so there's some conversions here. You can go through these slides at your leisure here. And these are just practice and some examples of it. This is one thing, though, that I want to talk about, and that's inputting numbers that are in scientific notation into your calculator. And sometimes people use the 10 to the x key for this. I recommend not using the 10 to the x key. I recommend using the EE or the EXP key or the scientific notation key, because when you hit this key, it automatically puts in times 10 to the x, and then you just input x. That's it. But sometimes people miskey it. That is, they'll use the 10 to the x key and this, or they'll just use the 10 to the x key and their answer is off by an order of magnitude. Let's say they're supposed to get 10 squared, they end up with 10 cubed, or 10 to the first. And so, if you notice you're off by an order of magnitude, it could be because you're inputting it into your calculator incorrectly. In math, we just have the number. In science, we have the number and the unit. The number they call the value here, you don't have to worry about this. This is not important. And so if we have a quantity like 50 minutes, then there's the value 50 and the unit minutes. Or just the number and the units. I call this the number, not the unit. And so in science, we express things in terms of numbers and units. Everything. And so here's a simple calculation. How many seconds are in 50 minutes? And so this is the typical way we do calculations, and we use something called dimensional analysis or factor label. And that is, we know that there are 60 seconds in 1 minute. And so if we take this ratio, then we can get the minutes to cancel, and that leaves us with seconds. So if we take 50 times 60, that gives us 3,000, excuse me. And then the minutes cancel, that leaves us with seconds. So we have 3,000 seconds. They call this dimensional analysis because the units here, minutes, seconds, these are called dimensions. And analysis is we're just trying to get it to cancel to get us the correct units or dimensions. So here's another example of a dimensional analysis problem. The oldest horse racing track in the United States is the 8-furlong Pleasantation Fairgrounds racetrack in California. I wonder, is it Pleasantation or Pleasanton or something? What is the length of the track in rods? So 8 furlong rods. I don't know the relationship between furlongs and rods, but they give it to us here. There are 0.025 furlongs in 1 rod. And so we can have that relationship. Sometimes we change the relationships a little bit. And so the first thing is, how do we relate rods and furlongs? Well, we can relate it like this. So there are 0.025 furlongs per rod. Or we could say that 1 rod is 0.025 furlongs. Sometimes we don't like to do this in this fashion, like have these. So if I take this, I can move the decimal over and get 40. If I do 4 times 0.025, what does that give us? 4 times 25 would give us 100. So if I do 4 times 25, I get 0.1. Do you see that? 100. So if I do 40 times 0.025, that will give me 1. And so I'll multiply both sides by 40, top and bottom. So another way of looking at this would be, or 1 furlong per 40 rods, or 40 rods per 1 furlong. These all share the same ratio. When we have a ratio like this, we call it an intensive property or intensive quantity. Intensive means it doesn't matter how many rods or furlongs, the ratio stays the same. Let's say I had 1,000 furlongs. Is that ratio going to change? Or let's say I had 400 rods. Will the ratio change? No, the ratio doesn't change. You know, it's like 60 miles per hour. 60 miles per hour is what we call an intensive property or intensive quantity. So 60 miles per hour. Let's say I drove 1,000 miles. Is it going to change? Let's say I drove 1,000 miles at 60 miles an hour. Does that change the ratio, 60 miles per hour? No. And so intensive means it doesn't matter what the amount is. The ratio stays the same. That's intensive. However, this is what we call extensive, 8 furlongs. 8 furlongs, will that change? Right now I have 8 furlongs, but if I had 20 furlongs, is it still the same as 8 furlongs? No, that's different. You know, that's gallons of gasoline. How many gallons of gasoline does it take? Well, that's extensive. It depends. Well, how far do you want to go? So normally when we do a dimensional analysis problem like this, we like to start off with the extensive quantity, which is 8 furlongs. And then these intensive ones, these ratios, we just use to relate things. Sometimes we will start off with intensive, Like, for example, if I'm driving 60 miles an hour, how many kilometers per hour is that? Then we might start off with an intensive 60 miles per hour and then convert that to kilometers per hour. I had to do the reverse because I was using my sister's car. I don't know why she has the speedo set to kilometers per hour, but she lives in Wyoming, so maybe it's closer to Canada, so that's why. So I had to convert it from kilometers per hour to miles per hour. Somebody was saying, you're going too fast. This is only like a 25. I was going 50 kilometers an hour. And they're saying it's too fast, but they were thinking miles per hour. It was actually pretty slow. All right, so here we can, even though I have no idea these mean or whatever, we can use one of these ratios here. And in dimensional analysis, what we try to do is we try to cancel out the unit. So here, I want to cancel out furlongs, and then I'm going to replace it with it. And so if I want to cancel out furlongs, then these two are appropriate here. So I could either use 40 rods per furlong, or I could use 1 rod per 0.025 furlongs. Well, they used it here. I probably would have done 40 rods per furlong. And so 8 times 40 gives us 320 rods. Now, we also have something else that we got to worry about. It depends on how precise this 8 is. This racetrack, is that exactly 8 furlongs, or is it approximately 8 furlongs? When we take a measurement, can you take an exact measurement? Let's say this is one of the other arguments for Dalton's atomic theory. Let's say you need to mix sugar and flour in a 2-to-1 ratio, and it has to be exactly 2-to-1. Is that something that is easy to do? It's not. It's not, because there's going to be some uncertainty. Did you get a little bit too much sugar, a little bit too much flour, or not enough? Is it always going to come out exactly 2-to-1? Because water always comes out exactly 2 parts of hydrogen to every 1 part of oxygen, no matter where you get that water from. The water could be from California, it could be from New York. It's going to have the exact same 2-to-1 ratio. Is that something that's going to be easy to do if matter is infinitely divisible? If matter is infinitely divisible, you might get a little bit extra hydrogen or a little bit extra oxygen one time. The next time you might make up for it. But each time to get that consistent 2-to-1 ratio, it's hard to describe that in terms of infinitely divisible matter because of how things react. It's more random how they react. And so, is this exactly 8 furlongs or approximately 8 furlongs? Because normally when we do a measurement, we say, okay, that's about 8 furlongs. What does that mean? That means it's anywhere from about 7.5 to about 8.4, something in that range, because we call that precision. How precise is that measurement? That's the oldest racing track in the U.S. Maybe that's exact, because I have no idea what a furlong. Does anybody know what a furlong is? I have no idea. So maybe that's exactly 8 furlongs. If that's exactly 8 furlongs, then there's no uncertainty there. That means we have exactly 8 furlongs, and that means we'll have exactly 320 rods, because I imagine this is exact too. But what if it were a measurement? What if somebody went out there and started measuring? Maybe this is a furlong stick or something like that, and they're measuring it. And they measured it at 8 furlongs. Then there's a lot of uncertainty. So in that case, what we say is in approximately 8 furlongs, there are approximately 320 rods, but we need to specify that or write that differently. It's like this. When I was talking about 18 karat gold is 80%. So is that approximately 80%? Or how precise is that? And so, um, we have different ways to express this. So if I say my 18 karat gold were 80% versus 80% versus 80.0%, then what we're looking at is we're looking at varying degrees of uncertainty. This one is the most precise, which means that it's going to have the least amount of uncertainty there. This one is the least precise, which means it has the greatest amount of uncertainty. And the amount of uncertainty we can either do like the book does. The book does, they'll call this anywhere from 70 to 90%. Or like I do, I take half the smallest. The smallest, this is going by tens. So we go 10, 20, 30, 40. And so if we're counting by tens, then this could be anywhere from 75 to 84% if we're counting by tens. If we're counting by ones, then we get a little bit more precise. If we're counting by ones, then this could be anywhere from 79.5 to 80.4, because I take half of 1, which is 0.5. If we're counting by 1/10, so this would be 0.1, 0.2, 0.3, then if I take half of that, and this would be between 79.95 and 80.04. Do you see how much more precise that is? Does that make sense for that? So the situation is this: how precise is the definition? You know, the definition might be exact. 18 karat gold might be exactly 80%, but how is it possible to get it exact at exactly 80% to the nearest atom? No. And so what we do is, well, it depends on how precise the manufacturer, who made the 18 karat gold. You know, what's their standard of precision? And so if you were to buy it, which one would you buy? I'd probably get the 80.0, because if you buy this, you might have only gotten 75% gold. And if you only get 75% gold, then you got 5% less gold than what you're supposed to have, but it still rounds to 80 if you count by tens. And so you would start to worry about like maybe unscrupulous vendors. You might have to worry about that. We have different standards for things, and it depends on the precision of those standards. So for example, milk has to have a certain level of protein. If it doesn't meet that level, then you can't sell it as milk. So for example, this prevents people from watering it down. Let's say you have a gallon of milk, but you want to make it 2 gallons. We'll just add a gallon of water and just water it down and then sell it as regular milk. Did you hear about the pharmacists? Actually, there have been multiple cases where pharmacists have watered down the medication. You know? So for example, there's one pharmacist, I think it was in California, who watered it down. So he cut the concentration in half. Doubled the profit, because now you could sell it for twice as much. Does that make sense for that? Yeah. Really, can you believe it? Yeah, especially a chemotherapy agent. I mean, some people are relying on this for their life. I couldn't imagine that, but fortunately, they were caught cheating like that. But other people have been caught because of deaths. Did you hear about the pet food scandal? The pet food has to have a certain amount of protein in there, and measuring the protein, because proteins, there are lots of different kinds of proteins, is difficult. And it's like separating the mixture. Separating the mixture is not so easy to do. So instead what they did was they analyzed the pet food for nitrogen content. And they figured, well, there's nitrogen in a lot of proteins. If we figure out how much nitrogen there is, then they can correlate that to how much protein was in the pet food. Well, unfortunately, some unscrupulous pet food manufacturers, or it might not have been the manufacturer, it could have been the distributor or maybe the pet food shop. I don't know exactly. I think it was the manufacturer though, or the importer. But anyway, to cheat the system, there are other things that contain nitrogen. And do you know what else contains nitrogen? Is like, have you ever seen those plastic plates that they have in some restaurants? Those are made out of melanin plastic, and those contain nitrogen too. So what they did was they ground up melanin and put it in the pet food. And unfortunately, melanin's toxic for pets, so the pets ended up dying. And let me see if I have that story. Are you guys familiar with that? It happened a long time ago. This is an article in 2017, so it happened in 2007. 10 years later, now it's longer than 10 years, but examining the pet food industry a decade after the widespread melanin contamination. The contamination was done on purpose. It was done on purpose to boost the protein level of the food. But what clued them in was the deaths of 14 cats and dogs eating the same pet food. So unfortunately, that's it. So we have certain standards, certain ways of dealing with stuff. And so they were trying to meet the protein levels, get it within the standard. So I don't know, maybe this is exact. And so if this is exact, then this would be exact. Very precise, no uncertainty there. However, if somebody just measured it, you don't know. They didn't measure it to 8.0, 8.00. If they did, then that would be more precise. So what we do is, in science, we take this, how the number is written to give us clues. So this might mean exact, or it might mean uncertain. If you only have one digit like this, it's very uncertain, 7.5 to 8.4. It's very uncertain. We'll talk more about the uncertainty later, and that's related to sig figs. For right now, we're going to ignore the sig figs. That is, sig fig stands for significant figures, and that's the way we track precision. So we'll talk about that later. Normally, when we take measurements, like if I measure 8 furlongs, I worry about certain things. And so when we take measurements, we're concerned with systematic error. You know, systematic error. If I'm measuring something 8 furlongs, or how does systematic error impact that particular measurement? In other words, systematic error is related to what? Usually equipment or user. So if the user is systematically reading a meniscus too low or too high, that's always going to lead to the same error, right? It's a systematic error. And how do we fix systematic errors? The error, even though I talked about that stuff in lab, like systematic error, random error, this is stuff also in the book. And so lab stuff, a lot of people ignore it. It's because they think, oh, okay, the lab stuff usually doesn't show up on the lecture test. There's normally a separate test for lab. But in this class, sometimes the lab stuff shows up on the lecture. So it's probably best not to review it the night before the test. You know, systematic error. If I had some questions on systematic random error, would you be able to answer those on the test? Or maybe not right now, but when are you planning to study that stuff? The test is next week. You know, maybe the night before the test. Let's study that. Some of the lab stuff deals directly with lecture stuff, and other stuff is just related to lab. So sometimes the lab question will pop up, since the question was asked what's on the test and the format and that kind of stuff. We'll talk about that later.
So how do you fix it? Is it like 50% error?
Yeah, how do you fix systematic error? We do a process that starts with a C. I don't know, does anybody remember what process starts with a C-A-L? C-A-L. Calibration. We fix it by calibration. So if somebody's measuring furlongs, we got to make sure the furlong measuring tape is properly calibrated. Right? It's not measuring in error. And so this is usually an easy fix. And then, and so as long as we make sure everything's calibrated, we're okay. But even if everything's calibrated, there's another error that might pop in there. What's that other error? Random error. Now, what do we do with random error? You know, this is like throwing the darts or measuring something. You know, sometimes we measure it and then it comes out a little longer. Sometimes it comes out a little shorter. You know, if you're measuring a racetrack, are you going to be able to get the exact same measurement each time, do you think? I mean, a racetrack, how wide is it and how far does it go around? You know, are you going to be able to position everything exactly the same each time? Maybe, maybe not. And so there could be some random error associated with that. Now, random error is sometimes it's a little high, sometimes it's a little low. And so what do we normally do with random error? For random error, we normally do multiple trials. So let's say your density was a little high. Maybe the next time you measure it's a little low. So one time it's a little high, the next time it's a little low. If you average the two, you'll come up with a better value. And so in theory, if we take an infinite number of measurements of the density of water, some are a little high, some are a little low, those random errors will cancel each other out and give us our what we call the true value of water. But, you know, 3 was enough. How many is optimum? So let's say I took 1,000,000 measurements of the density of water. That's good. That would be very good. But is there much benefit to going to 1,000,001? So if I took 1,000,000 versus 1,000,001 and average, am I going to see a much better result with 1,000,001 measurements versus 1,000,000? No. It would be the law of diminishing returns. So in order to maximize the amount of returns, we're not going to take an infinite number of measurements. We're going to compromise. And the compromise usually results in most scientific measurements are done 3 times, and we'll just take the average of the 3. And there's statistics that back this up. In other words, statistically, we're going to get the best return on 3 measurements. Because 1 measurement, you're really subject to random error. You know, it could be way off, it could be right on. Who knows? It's just 1 measurement. So you take a second measurement, then you kind of know, where maybe the ballpark, if they're similar or way off. And then you take a third measurement, and that's going to improve it. And so we should know ballpark where it should be. And then we take a 4th measurement, a 5th measurement. And so the greatest benefit comes in at about 3 measurements. So when things are hard to measure, we'll just take 3 measurements. If things are easy to measure, then you can take thousands of measurements because they're easy and quick. And so you'll see that as well. But anything that's hard to measure, the minimum number of measurements you want is 3. And then we can minimize what? Or try to minimize what kind of error? By taking 3 measurements, we're trying to minimize random error by averaging the 3 measurements. So we do that. All right. Also, when we do measurements, we talk about uncertainty. How much uncertainty. And that's related to precision and accuracy. And so those are things. And so in this chapter, we're going to be talking about those in more detail as well, but later on. All right, so when we're doing these calculations, we come up with equivalency and conversion factors. You don't have to know the definitions of those or the details, but for each equivalency, we can get 2 conversion factors. So here's our equivalency. 1 day is 24 hours. Is there any uncertainty there? are some days longer than 24 hours or some days shorter than 24 hours? Well, it depends. They're saying that the Earth is slowing down, so days are getting longer. Is that right? Have you heard that? But we're going to ignore that. Our definition is a day is exactly 24 hours. So there's no uncertainty there. And so we have two equivalencies here. One day is 24 hours, or there are 24 hours in one day. So that's it. 17 miles to the gallon. Is there any uncertainty there? That's exact. We get exactly, your car gets exactly 17 miles to the gallon. What do you think? If you measured your fuel efficiency and you measured it at 17 miles a gallon, a lot of you don't have to measure it. It depends, you know, what kind of car. Like my car tells me that. I have a gasoline car. I have an electric car too. In the gasoline car, it's telling me my fuel economy. I don't know how frequently it samples, but do you think that's exact or approximate? It's approximate. And so this is not exact. So what we do is, the top one here we call a definition. By definition, there are 24 hours in a day. And that's exact. This is just a measurement. Somebody measured that they were getting 17 miles per gallon. There's uncertainty associated with that. Now, the precision that they stated will tell you how much uncertainty. So they have 17, so that's plus or minus half. They're measuring it to the nearest mile. So we take half of it. And so we say that 17 means anywhere from 16.5 to 17.4. That would be the range of uncertainty. However, if they measured it and they got 17.0 miles per gallon, that's more precise. That's less uncertainty. And that would be, they're measuring to the nearest tenth. And so half of a tenth of a mile would be 500ths. And so it would be plus or minus 0.05. And so it depends on how precise they measure it. That will give us an idea of uncertainty. And we call that sig figs. So if I measure this to 2 sig figs, then I'm going to get this kind of precision. If I measure this to 3 sig figs, like 17.0, that gives me more precision. And so the number of sig figs will tell us how precise we can be. And the precision tells us a range uncertainty, you know, how narrow the range is or how wide the range is. And so we'll be incorporating those into our calculations. So we're going to go to quantitative calculations. And this is the algorithm. My algorithm is a lot simpler than this algorithm, so I'm going to skip this algorithm entirely. So calculate the number of weeks in 672 hours. 672 hours is extensive. We usually start the problems with extensive. Given 672 hours, and what else are we given? We're given 24 hours in a day and 7 days in a week. All right, so we'll start off with 672 hours, and then my algorithm is this. I want to cancel out hours. So if I want to cancel out hours, I'll put hours in the denominator. And so where can I go from hours? I can go from hours to minutes. So if I go from hours to minutes, I can go, there's 60 minutes per hour. But if I go from hours to minutes, is that getting me closer to weeks or further from weeks? It's going further from weeks. And so if I go hours to days, that's better. So we'll go 24 hours in a day. So I'm not going to go hours to minutes, although I could. All right, so the algorithm is I just want to cancel out the hours, and that leaves me with days. And then I repeat this. So I have days here. I need to go. So should I go from days to months? See? 1 month is 30 days. Or should I go from days to weeks? I'll go days to weeks. So altogether, 672 hours turns out to be 4 weeks. Now, this 672, we got to think, is that exactly 672 or approximately 672? What I mean by approximate is this. If it's approximate, then that means we look at this this is measured to the nearest hour, so we'll take it to plus or minus the nearest half hour. So if we take it plus or minus the nearest half hour, it'd be 671.5 to 672.4 hours. If that's the case, there's a little bit of uncertainty here. If there's a little bit of uncertainty here, that means there's going to be a little bit of uncertainty in the number of weeks. However, if this were exactly 672 hours, then is it exactly 4 weeks? And so this is what we do here. So we'll go ahead and do this calculation. The calculation would be 672 divided by 24 divided by 7. And that gives me 4. And so there are two ways we express this answer. One way is that if there's no uncertainty here, we'd say in exactly 672 hours, there's exactly 4 weeks. Or if we were saying it's approximately 672 hours, then what we would say is that there are approximately 4.00 weeks. This is measured to the nearest tenth, nearest hundredth of a week. So we take half of that, which would be 5,000th of a week. So this would be plus or minus 0.005, half of it. And this would be plus or minus 0.5 hours. And so there's going to be a little bit of wiggle room here, a little bit of uncertainty, whereas over here, there's none. And so it depends on where this 672 came from. If this 672 were measured, do you think somebody's standing there with a stopwatch and going to hit it exactly when it gets to 672? Maybe they did. Maybe they didn't. If you're going to measure how many hours, 672 hours is a long time. Sit there. And you hit it right at the 0. Boom. It's there. Or, you're watching that second hand, or approximately. And so we don't know. So this could be a hypothetical. In all measurements, there's uncertainty. But if this is like a thought experiment, if I had exactly 672, which would be a hypothetical, then I'd have exactly 4 weeks. But if this were a measurement, then we take that as a measurement. This would be a measurement. I got it, 672 hours to the nearest half hour. Okay, that's good enough. And that means the weeks are going to be to the nearest whatever, 0.005 weeks, plus or minus. What distance expressed in miles would an automobile travel in 3 hours at an average speed of 62 miles per hour? All right. So this is also can be thought of in terms of a hypothetical. So hypothetically, if you traveled exactly 3 hours at exactly 62 miles per hour, what distance? Are you going? Or this could be measured. I drove approximately 3 hours at approximately 62 miles. Approximately how many miles did I drive? 62 miles per hour. And so we're thinking in terms of uncertainty here. And so if we do this exact, then there's no uncertainty here. This is exactly 3 hours. And if we do this as exact, this is 62 miles per hour exactly. No uncertainty there, it's exact. Then we're going to travel exactly 186 miles. If this were approximate, okay, this 3 hours, let's say I kind of measured it, I kind of didn't measure it, and so the uncertainty here is going to be between 2.5 hours to 3.4 hours. So 3 hours plus minus a half an hour. I didn't really keep track of my watch. So I drove. Approximately how many miles did I go? Well, in that case, it would be closer to maybe 200 miles plus or minus 50 miles. And so we want to keep track of this uncertainty in the calculation by keeping track of something called the sig figs here. And so this is not following the sig fig rules unless these were exact. Because since all measurements contain uncertainty, then this final answer can't be this exact, can't be this precise. It's to be approximate. Well, anyway, this is the dimensional analysis, or sometimes it's called the factor label. But we need to get hours. And so here, I have choices. So I'm going to get rid of hours. Should I go to minutes? Maybe, maybe not. Should I go to days? I can go from hours to days. No. In this case, I'm given something more specific. And the specific one I'm given, I can relate hours to miles. But this one's only valid for this problem. You know, hours to minutes is valid for any problem. Hours to days is valid for any problem. But hours to miles, it depends on how fast you're going. So this, what we call conversion factor, is valid just for this particular problem. And how precise is that? You know, when you tell somebody you're driving 25 miles an hour, does that mean you were driving exactly 25 miles an hour or just about 25 miles an hour? You mean, are you glued to the speedometer and it's not moving at all? Or, yeah, it's about 25 miles an hour. Well, most people will say, yeah, it's about 25 miles an hour, which leads to uncertainty. And there should be uncertainty in the distance because you weren't watching it closely enough. Here, if this person, a little girl broke her piggy bank, inside she found 2,608 pennies. How much uncertainty is there? Do you think they counted like plus or minus 50? No, this would probably be exact unless they miscounted. So in this particular measurement, you can't get half a penny, or there isn't going to be that level of uncertainty. The only uncertainty would be if they miscounted, but they probably should count it at least maybe 3 times, and then maybe they counted too many one time, too few another, and that random error might average out, because that's a lot of pennies to count. 2,000, almost 3,000 pennies. And so here we could say that let's say there's no uncertainty here. Is there any uncertainty here? 100 pennies and $1. There's no uncertainty there, so there's no uncertainty in this. This is going to be $26.08. That should be exact. So not all, in fact, most of the problems aren't going to be this easy. This is called a one-step conversion. The problems typically are going to be multi-step conversion. But multi-step conversion are just as easy. It's just each individual step is just as easy as this. It's just stringing them together that's the hard part. And so this is like, I was watching this thing about climbing Mount Everest. And they were talking about, how difficult it is. And they were saying, they go 10 feet in 1 hour. They take one step up and rest. And then another step up, rest. And so each step they took a long rest. Well, that's the same thing here. You do a hard problem, it's just stringing these together. So you do one step, and then if you get stuck, take a rest, and then see if you can figure out what the next step is going to be. That's it. So we're going to go, there are a lot of slides here, over 60, so we're going to go through most of these pretty quickly. But we have the metric system, and we have something called SI units, which is the International System of Units here, SI. We have base units, which we'll talk about, the SI base units here. Actually, before we get to the base units, let's talk about the metric prefixes. Kilo is one, milli is the other. These two are very common, kilo and milli. But we talked about some of these already. Some ones that you want to memorize are kilo for sure and milli. What are some others that are common? Centi's very common. You should memorize that. Deci, if you're a biologist. Biologists use deciliters a lot more than chemists. But we're not going to make you memorize that. Micros, common. Nanos, common. pico is common. Atoms, molecules, big molecules, like proteins are nano scale. Atoms are pico, hundreds of picos, meters scale. And then there's one more. There's one more that I talked about. Do you remember which one? It's smaller than a pico. Two more that are smaller than a pico.
Is it atom? Is that-
It starts with Z.
Starts with what?
Does it start with Z?
Z? Well, the next one starts with an F. Hmm? Femto. Femto. It used to be femto is important because femtosecond lasers, but now it's been surpassed. So femto would be the next. Femto would be 10 to the minus 15. And 10 to the minus 18 is called, starts with an A.
Wait, I thought it was like -6.
Atto. Yeah. Good. Atto. What's significant about atto? An attosecond. So, for example, if you blink your eyes, how long do they stay shut for? Not very long, but if you blinked your eyes and something went fast by you, you'd miss it entirely, right? And so, if you're watching a chemical reaction and you blink your eye for a picosecond, you missed it. It's already passed. It's already gone. If you're watching a chemical reaction and you blink your eye for a femtosecond, it's already gone. It's already happened. But now, if you could blink your eye just for an attosecond, you would be able to see it. And that's what the 2023 Nobel Prize in Physics was awarded for. The 2023 Nobel Prize in Physics was they were able to make a laser that blinks its eye for just an attosecond. Because all the other lasers blink too long. And so if you're blinking or pulsing, they call it pulsing. If you're pulsing the laser at a picosecond interval, its eyes are shut for too long. It's going to miss the reaction. And so the attosecond laser will catch the reaction as it's happening. Of course, we blink our eyes much longer, so we don't see it, happening in real time. We just see the before and the after. That's it. Are we going to use it? Nah, not really. These ones in blue are the most important here. Those ones you should have memorized. I guess we'll talk about SI units a little later. The order of this is going to come back to SI units. We know the difference. You guys know the difference between mass and weight? Yeah, okay. Know the difference. We measure mass and weight with balances. Since we live on Earth and the force of gravity doesn't really change, it's a constant, then we use it interchangeably, mass and weight. But they have different units. The units that we use for mass are typically in what? Grams and kilograms. The unit that we use for weight is typically in pounds and ounces. Even though the weight varies depending on gravity, we aren't leaving the surface of the Earth, so we don't have to worry about it at all. Which brings up this video I saw the other day. I was watching this. I haven't gone through the whole thing, but this person here, Avi Loeb, he's a professor at Harvard, studying astrophysics, I think. But apparently there was this object that passed through our solar system. It was interstellar, meaning it came from some other place outside our solar system. Interstellar object. And it had some very interesting properties that were never observed before. And he came up with a hypothesis. He hypothesized that this object was actually made by aliens, or at least an alien. Since nothing like this has been observed, the only thing, well, things like it have been observed. You know, things like an old fuel booster from one of the space missions was like it, the way it interacted with light. And so based on certain observations, he proposed it. But, you know, some people will say, man, aliens. What do you think? I think it's pretty interesting, but should this person be fired from their job at Harvard? I mean, no. This person has some pretty compelling reasons to believe. I mean, of course, there are competing hypotheses. Competing hypotheses is that's not an alien object. You know, that is a island of hydrogen. But he has an argument against that, and that is, if it were an island of hydrogen, it would have vaporized, you know, considering its path it's traveled. And so an alternative hypothesis that was proposed is an island of nitrogen. And so there are a whole bunch of alternate hypotheses, and he goes through those one by one and says, well, you know, those don't make sense, basically. And although, you know, what do you need for proof? This is like Dalton. Dalton's trying to prove the existence of atom, but atoms are like aliens. Has anybody ever seen an atom in Dalton's time? So Dalton's like the person who's saying, well, aliens exist. And then there are a bunch of skeptics saying, well, I've never seen an alien. If you want to prove it to me, show me an alien. I need to see an alien coming out of a spaceship. You know? But there's some pretty compelling evidence for this, and that it has to do with the structure and the types of rocks and the things that exist. So this is pretty interesting. Well, I was watching this, and then another one came up, about aliens. And have you ever heard of this person by the name of... wait. Have you heard of Area 51? And have you ever heard of this person, Bob Lazar? Bob Lazar is this person who came up with this hypothesis. Bob Lazar apparently is a MIT and Caltech trained scientist who was hired by Area 51, and he worked in this part of Area 51 called S1. And S1, they have a bunch of alien spacecraft there. And his job was to reverse engineer the propulsion system of the alien spacecraft. And his thing is, he was talking about element 115. He was saying that if you take element 115 and you bombard it with protons, then it contorts gravity. When you contort gravity, then you can defy the laws of Newtonian physics. Newtonian physics relies on gravity, right? The apple falling from the tree and this kind of stuff. And therefore, you can get space vehicles to travel in ways that seem to defy physics because of the way they interact with gravity. But that's fine. You know, it's good to have competing hypotheses or hypotheses on certain things, but you know, the hypotheses need to be supported by what? They need to be supported by observations. So there's a good quote in Ari Loeb's. In Ari Loeb's, he said, experiments are the key to expanding knowledge. You know, that totally makes sense, because experiments, you get the observations, you expand scientific knowledge. But there are some things here that cannot be backed up by observations because one, element 115 at the time Lazar proposed it wasn't yet synthesized, but people have synthesized element 115. Element 115 has extremely short half-life. That is, it's extremely radioactive. It doesn't last for very long. And then the properties, when you bombard things with protons, we've bombarded lots of atoms with protons to see what happens. In fact, that's called a nucleosynthesis. And you end up making other things, but not necessarily by contorting gravitational fields. So the observations in support of Bob Lazar versus the observations in support of Avi Loeb are totally different at different levels. But this is the way science is supposed to work. Science is you propose hypotheses and then you support that hypotheses using experimental observations. Avi Loeb didn't just propose that this object's Mona Mona or something like that. It's a really weird object. But he said an alien space probe could have landed on Earth. Have you heard of that one too? I guess in 2014 there was a meteorite. Most meteorites come from the solar system here, but this one was interstellar. It came from outside and it was moving very fast. Most meteorites break up high up in the atmosphere. This one survived until low in the atmosphere. So this was a much tougher meteorite. And then he went to go collect specimens off this, the debris field. And so he had an expedition last year or the year before out to the ocean and scrape the ocean to collect these little pebbles and then had those analyzed. And when you compare the elemental composition of the pebbles that he collected versus the elemental composition of all the meteorites that have been studied so far, it was totally different. It's a very unusual alloy. And so in that sense, it is alien. Nothing like that alloy has been found. So this is pretty interesting stuff. But fortunately, he's still working. He hasn't been fired. And it's very interesting. So getting back to this here. So the SI unit of mass is a kilogram. This is the quantity of matter. So that doesn't change with gravity. You're going to have a certain number of atoms in there. How many atoms is that? Well, how many atoms is that we need to define? So how is a kilogram defined? And so let's talk about that. This is the definition of a kilogram. Do you see in here? This is a block of platinum and iridium. Iridium has a very interesting history too. Most of the Earth iridium, do you know where it came from? They came from a meteor. And this meteor crashed in the Yucatan Peninsula and vaporized, spreading iridium across the surface of the Earth. So there's a very thin layer of iridium around. Apparently, they suspect that this meteor caused the demise of the dinosaurs. And so that's it. But anyway, iridium and platinum are what we call noble metals. And what are some of the properties of noble metals, like gold? Gold is another example of a noble metal. They're great conductors, yeah. And there's something else about, like iron is not considered a noble metal. They don't oxidize easily. They're very difficult to oxidize. And so like gold maintains its luster, platinum maintains its luster. We use those in electronics, but they're still worried about oxidation. So this is why there are 3 bell jars here. The 3 bell jars is to make sure that there's no oxygen that gets in here. Even though iridium and platinum are very, very resistant to oxidation, there's still potential it might get oxidized. And if it gets oxidized, what's going to happen to the weight of this, the mass of this? It's going to change. And in fact, the mass will increase if we form a coating of oxide. And so this is the definition of a kilogram. The definition of the kilogram is this chunk of metal here weighs exactly 1 kilogram. There's no uncertainty. This is exactly 1 kilogram. Now, we need to calibrate our balances, so we would like to use this, but we can't because this standard is locked in a vault in France, and so nobody can touch it. So what we have is we have a clone, but do you think they made the clone exactly the same as this? No, it's probably going to be off a little bit, you know, a few more atoms of iridium, a few less atoms of platinum or something in there. And so the clone is not going to be exactly the same, but it's close enough. And those clones can be cheap, depends on what they're made out. Do you think our clone is made up of platinum and iridium? No, our clone is made up of stainless steel. Stainless steel is problem. I heard like the Tesla, you know, the Tesla Cybertruck's made out of stainless steel. And I guess people are complaining that it's starting to rust. Have you heard that? Yeah. They probably used 430 stainless steel. They have a bunch of different stainless steels out there. If they used 304, it shouldn't have rusted this long. And then they should have known better to use a different alloy, 300 series or higher. Like 316 would be surgical stainless steel. That's not going to rust. So if they made the Cybertruck out of 316 stainless steel, that wouldn't have rusted at this short of a time period. And so it's sounding like they used the cheaper stuff, unfortunately. I mean, still kind of cool. They use, like the DeLoreans. You know the DeLoreans are the other stainless steel car. The DeLoreans, those I don't think have rusted much at all. So those are probably 304. And then Rolls-Royce has that Silver Phantom with a stainless steel hood. Have you seen that one? Yeah. That one, if that one started to rust, you know those customers, after paying, I don't know how much, $500,000 for that, would be pretty pissed off. But anyway, this is protected from this. Now, it says a kilogram weighs 2.2 pounds. Do you think, is that exact? It turns out that's not exact. So what we do is, there's uncertainty here. This is going to be anywhere from 2.15 to about 2.24 pounds. We can be more precise. And what I want you to do is I want you to be 4 significant. This is what we call 2 significant figures of precision. We should know this to 4 sig figs. So 1 kilogram is equivalent to approximately 2.202 pounds. And so this is being a lot more precise. There's a lot less uncertainty here because this is going to be anywhere from 2.2015 to 2.2024 pounds. And so this is being more precise here. But this is not exact. And so what we say is it's approximately. But this is, both of these are approximate, but this second one is much more precise. Here. Now this other one is this. Some people don't like it like this. Some people like the relationship between pounds and grams. And so there are 454 grams per pound. Okay, this is what we call 3 sig figs here. This is what we call 4 sig figs here. We like 4 sig figs minimum, that level of precision. This isn't precise enough. So it turns out it's 453.6, but this is still not exact. Is a pound, 1 pound. And so we either use this one or this one. But I don't use both because they're essentially saying the same thing. You can figure it out. And so normally I just memorize this one. I have this one memorized too, but this one's easier to memorize, 2.202. If you're going to memorize it. Uh-huh.
What do you mean memorize it? Because you'll have like a sheet on the test? Or?
You'll have to memorize the exact ones. The exact ones are what we call definitions. So you'll need to know the definitions. 4 quarts in a gallon. You know, 2 pints per quart. 2 cups per pint. You know, those types of things are definitions. Some of these, there are 2 that aren't, we use these a lot, so that's why I have it memorized. It's just by repetition. I didn't purposely go out to memorize it. It's just you use it so many times, it just sticks in memory. All right, then we have length. This is a definition. This one you have to memorize. So 1 inch is defined as 2.54 centimeters. Definition, we use these 3 lines here. So this is by definition. And so this is exact. In exactly 1 inch, there's exactly 2.54 centimeters. There's no uncertainty there. Exact. All right, so we'll take a break right now, and then let's start up again in 15 minutes. So 3 o'clock. The SI unit for mass is kilogram, but chemists use gram. We call gram a derived unit. It's derived from the kilogram, and it's 1/1000th of a kilogram. The SI unit for length is meter, but we typically use like centimeters and millimeters. Centimeters and millimeters would be derived units. We can derive those from meters. Or we use inches. Inches as well would be derived units. And to derive those, we need relationships. These are the relationships. So here, the relationship between inches and centimeters. This one you'll have to memorize. Other ones you'll have to memorize, like, for example, centimeters and meters. How many centimeters are there in a meter? Centimeters in a meter. 100. So maybe you already have it memorized. If you don't have it memorized, you should memorize that one. So there are 100 centimeters in a meter. Okay, we use those relationships to get our derived units. The SI unit for volume is also derived. It's derived from a base unit. The base unit of length is a meter. The SI unit for volume is a cubic meter. So you take a meter length times a meter width times a meter height, that gives us a cubic meter. So the SI unit for volume is the cubic meter, which is derived from the meter, which is the base unit. For us, a cubic meter is usually too big. A meter height with length is too big. So we use something smaller, like a cubic centimeter. And so we have certain relationships. One of the relationships is, this is by definition, 1 milliliter is exactly 1/1000th of a liter. Or we can multiply by this 1,000 here. So this is 10 to the minus 3. If we multiply by 10 to the third, that gives us 1,000 milliliters is equivalent to 1 liter. But this is exact here. 1 milliliter is exactly 1 cubic centimeter. And so the exact ones I'd like you to memorize. And so this one you should memorize. 1 milliliter is defined as 1 cubic centimeter. And we use this. And so we use these interchangeably. And so it doesn't matter which one you use, a cubic centimeter or milliliter, they're exactly the same. Then we might want to relate that to other things like a liter. If I have a liter, and there are 2 ways we can use a conversion factor like this. We can use it based on the definition of M. M is defined as 10 to the minus 3, so this is 10 to the minus 3. Or we can multiply by 1,000, so this would be just 1,000 milliliters is equivalent to 1 liter. So if I have 1 liter, this is a 1 liter box here. How many milliliters do I have in that? 1,000 milliliters. And so I'll have 1,000 of these little boxes, and each little box is 1 cubic centimeter. And so in 1 liter, I'm going to have 1,000 cubic centimeters. Here. And so this is what this is illustrating here. Now, we do some other derived units, and the derived ones, hopefully we don't have to memorize them, we can derive it. So this one we have to memorize. This is the definition. This one, hopefully we don't have to memorize because it's derived, but if you have it memorized, that's fine. We do have to memorize the metric prefixes, so if we know that, we can figure this one out. But there are some other derived ones that we will be interested in. So for example, let's say I had 1 cubic meter. how many cubic centimeters are there? In other words, how many milliliters are there in a cubic meter? And so the way we derive this is we know the base. For example, 1 meter, and we know how many centimeters are in a meter. How many centimeters are there in a meter? There are 100 centimeters, and that's by definition. So if I have 1 cubic meter, are there 100 cubic centimeters in a cubic meter? No. How many are there? Do you want to memorize it? Not really. You should be able to derive it though. And so the way we derive it is this. We'll take our base one like this and then cube the whole thing. And so what that does is it gives us 1 cubed, meters cubed, 100 cubed, centimeters cubed. And so 1 cubed is just 1. And so in 1 cubic meter, there are 100 cubic centimeters. Do you know how much 100 cubed is? 100 times 100 times 100 is what? Or you could do 10 squared cubed. If you did 10 squared is 100, and then you cube it. And so maybe that might be easier. 10 squared cubed, cubic centimeters. What do you do with the exponents? Do you add them or do you multiply them? Oh, that's what you want to do for the math review. You want to review it a little bit. You multiply them. And so this would be 10 to the 6 cubic centimeters. Or it would be 1 million cubic centimeters. So if I had a cubic meter box like this, I could fit 1 million cubic centimeters in that. Exactly. Or 1 million milliliters. Since a cubic centimeter and milliliter are the same thing, that would be it. So this would be an example of a derive. So we should be able to derive these kinds of things from our base. So we try to minimize the amount of memorization and then just use a little bit of math to figure out the derived units. And so let's try to figure out one more derived unit here. And the one more derived unit is going to be this. In 1 square meter, how many square centimeters are there? Do you know the answer? 100 squared. 100 squared is 100 times 100, which is 10,000. And so in 1 square meter, there are 10,000 square centimeters. And so the way we derive it is 1 meter is defined as 100 centimeters. These are all exact. And so this is why I'm using by definition here. And so we square everything inside the parentheses. So 1 squared meter squared is equal to 100 squared centimeters squared. And so 100 is 10 squared, so this would be 10 squared squared. 10 squared squared, we multiply the exponents. And so this gives us 10 to the 4th square centimeters. 10 to the 4th is 10,000. 10 to the 3rd is 1,000. So this is 10,000 square centimeters. So in 1 square meter, there's exactly 10,000 square centimeters. So this is another example of a derived relationship or conversion factor. So we have to memorize these. These are probably the most common, 3 most common ones: kilo, centi, and milli. And so this is the way I like to remember it. Kilo is 10 to the 3rd, so 1,000 units per kilo unit. So 1,000 grams per kilogram. Centi here is 10 to the minus 1, but I mean 10 to the minus 2, but rather than do that, I multiply by 100. And so 100 centimeters per meter. And the same thing with milliunits. I don't like to use 0.001. I like to use 1,000. So 1,000 millimeters per meter or 1,000 milliliters per liter. And we can flip those over. So even though it's defined as 10 to the minus 3, I just multiply everything by 10 to the positive 3, both sides. And so we could do some conversions here. How many grams? In 0.711 kilograms. In 711 kilograms, we have this. This is how many sig figs. Do we count the 0 here or not? No, the 0 is what we call placeholder. If we wrote this in scientific notation, the 0 would disappear. So this is 3 sig figs. How many sig figs do I have here? In 1 kilogram, how many sig figs is that? Not 1. Not 0. If it's 1 sig fig, it's anywhere from 0.5 to 1.4 kilograms. So if I have 1,000 grams, is it anywhere between 0.5 and 1.4? Yes, it is, but is that being very precise? No, because we know that in 1,000 grams, I have exactly 1 kilogram. And anything by definition is exact. There's no uncertainty. If there's no uncertainty, how many sig figs do I have? Infinite. Infinite sig figs. That means I can put an infinite number of zeros here. That's the level of precision that I have. And the same thing here. There could be point in the infinite number of zeros here. And so anything by definition is exact. And if we have something that's exact, it has infinite sig figs. There's no uncertainty there. The number of sig figs is going to dictate, because the more sig figs you have, the tighter the precision you have. And so if you have an infinite number of sig figs, then there's no uncertainty. It's exact.
Values are precise?
These ones are by definition. Now the 0.711 might not be. This is probably measured. If it's measured, then there's some uncertainty there. It depends on how they measured it and what tool they used to measure it. And so what we do is we look at the precision as being half the smallest. The half the smallest is this is per gram. So it's plus or minus about half a gram, or 0.0005 kilograms.
What does that have to do with like the sig figs at the end?
The sig figs at the end. And so we have 3 sig figs here, and then at the end of this we still have 3 sig figs. So it's reflecting the same amount of uncertainty. You know, what some people do is they'll just write, okay, they'll just round this to 700 or something like that. If they round it, then they're introducing more uncertainty than what we had originally, you know. Or they'll write this more precise. For example, if they write this more precise, they might say 711.0. Well, we aren't allowed that level of precision, that level of uncertainty, because our original one had a certain degree that we have to maintain. So we're going to talk about sig figs in calculations coming up soon. So 5.25 times 10 to the 5th milligrams. How many sig figs is this? This turns out to be 3. The 5 is 1, the 2, and the 5. There's 3 sig figs. The exponent doesn't play a role, nor does the exponential, the 10. So we have 3 sig figs here. How many sig figs here? Infinite. This is by definition. There's exactly 1,000 milligrams in a gram. How many sig figs here? Infinite. So we had 3 sig figs here. Our final answer has 3 sig figs to reflect the uncertainty in this quantity here. There's no uncertainty here. There's no uncertainty here. And so what we're doing is we're converting. The conversions here, it's easier to go from milligrams to grams than straight from milligrams to kilograms, because I don't have that one memorized. So we go milligrams to grams and then grams to kilograms. Pretty straightforward. Here. A fruit drink is sold in bottles that contain 1,892 milliliters. Is that exact or 4 sig figs. In other words, is that infinite sig figs? It's exactly 1,892 milliliters. No uncertainty. Not a hair more, not a hair less. Do you think that's the case? No. This is probably 4 sig figs. And so there's going to be a little bit of uncertainty. So maybe some drinks have a little bit more, some drinks have a little bit less. At this level of precision, we expect a range from 1891 and a half to about 1892.4 milliliters. A milliliter and a cubic centimeter are the same thing. And so 1,892 milliliters is the same as 1,892 cubic centimeters. So what they're doing here is they're converting from milliliters to liters. So 1,892 milliliters is going to give you 1.892 liters. And here we have 4 sig figs here. We have infinite sig figs here. We end up with 4 sig figs here. That's what we do when we have multiplication and division, in this case division. So the way we write measurement is we're only allowed one uncertain digit. And so there's only one guess allowed per measurement, guess digit allowed per measurement. And so let's talk about the uncertain digit here in these examples. Whereas exact numbers, there's no uncertain digit. There's no uncertainty. Exact numbers are, you'll have infinite number of sig figs because they have no associated uncertainty. And the exact ones are by definition. And so most of the other stuff we can skip. So is this a very precise meter stick? This is a meter stick here. Is that very precise? Now, when we look at a measuring tool like this is much more precise meter stick. Do you see all the markings I have on my meter stick? This is much more precise. This is a higher precision. But is it accurate? Just because it's high precision, do you think this is very accurate? In order to determine its accuracy, I should do what? I should calibrate it. And if you look at my meter stick, do you see my meter stick is warped? Not only that, it's kind of old. Do you think this is measuring accurately? No, even though it's very precise, it's finely tuned, that is, it has lots of graduations, I don't know if it's reading accurately. But anyway, we're only allowed the one guess digit. And so what are we going to guess for this one? How long is this? This is 1 meter, I'd call that. Well, 0.5 would be halfway. What would you say this is? A little past 0.5? Maybe 0.6? Maybe 0.7? And so they did it here. Let's see what they measured for this. They said, well, okay, 0.6 or 0.7. It's kind of hard to say. And the level of precision here is, I try to get it a little bit narrower. And so they said 0.6 plus or minus 0.1. I usually take half of it. So if we're measuring to the nearest tenth, that is the nearest 0.1, then I take half of that, which gives me 0.05. So I say plus or minus 0.05. Because this one is a little bit too large. We should be able to be more precise in our measurements. And so when we look at this, if we say that this is 0.6 plus or minus 0.1, that means this could be anywhere from 0.5 to 0.7. Would you say it's close to 0.5 at all? Not really. And so this is why I narrow it down a little bit more. But it's okay. If you want to go the smallest unit is we're measuring this by 0.1 meters, then we'll just take that as the uncertainty there, plus or minus 0.1. That has pretty poor precision. This is much higher precision. Precision meaning we can narrow the range. Now, is there any uncertainty it's greater than 60? There's no uncertainty. It definitely is greater than 60. Can everybody see that? Here. So 60, we have no uncertainty there, but it's between 60 and 70, and that's where uncertainty comes in. So what would you guess? Would you guess it's 65, halfway between the two? No. What would you guess for this one? It looks like it's probably closer to 60, what? Maybe 63? Maybe 64? Something like that, 63 or 64. That's the best we can do. So we're only allowed the guess. The guess is going to be, well, they guessed it's 64. And here they're measuring it to the nearest centimeter, and so they're just taking it plus or minus 1 for that. So between 63 and 65, I probably would have narrowed this. I probably would have said half of that, and plus or minus 0.5. So if I do plus or minus 0.5, it'd be like 63.5 to about 64.4 in that range there. We'd expect it to be. So this is a little higher precision. We get more sig figs, less uncertainty. This is even higher precision here. Is there any dispute that it's greater than 64? No, so that's certain. It's 64. The guess comes in, where is it? Is it 64.5 right in the middle, or what? What would you call that? 0.2, maybe? So 64.2. And that's what they guessed. Or 64.3. 64.3 or 64.2 are good estimates. And so the guess digit is this last one here. Is it 0.3 or 0.2? And then they're just doing, we're measuring it to the nearest tenth, and so we're doing plus or minus a tenth here. All right, this is an even higher precision, meter sig. So this is the same one. Mine measures to the nearest millimeter, although I wouldn't trust its accuracy. So when I look at this, it's definitely greater than 64.0. Is it greater than 64.1? Yeah, there's no uncertainty. However, is it greater than 64.2? No. So it's between 64.1 and 64.2, and we call it, it's pretty close to 64.2. I'd call this what? Almost 64.2. And so I'm going to call it 64.19. Okay, that sounds good. So let's call this 64.19 centimeters. And so this is much higher precision. And then if you want to be consistent with the book, it's going to take the smallest. We're measuring it to the nearest hundredth of a centimeter. So we'll do plus or minus 0.01. Or the way I do it is I take half of that, and so I'd say plus or minus 0.005 centimeters, because I take a little more careful measurement, so I should be able to narrow it down even further, the level of precision. And so the number of sig figs is going to dictate that, the level of uncertainty in the range. This is wrong. 64.3, is that correct? It's totally wrong. And then they converted it to meters. These are totally wrong. They don't have the correct measurements for this. I don't know where they came up with these. But we got 64.19. All right, so what we need to do is, we need to calculate, you can calculate the number of sig figs. So we're only allowed one estimated digit. So the estimated digit here is 9. So how many sig figs do we have? 3. This preceding 0 is insignificant. The estimated digit here is 5, so there's uncertainty in that. You know, is it 4? Is it 5? Is it 6? Some uncertainty. How many sig figs do we have here? 2. These zeros preceding are insignificant. These are called placeholders. So that's 2 sig figs, that's 3 sig figs here. Now, what do we do with zeros following non-zeros? We'll talk more about that later. But we have to make sure we express things in the correct precision. So we have to do some rounding sometimes. Let's say this is too high of precision. Let's say the uncertain digit should be here at the 2. That means we have, this is uncertain, this is uncertain, we have too many uncertain digits. So we got to drop 3 of them. And so if we drop the 7, then we round up the 2. So this is why I went to 143 here from 142, because we're losing the 7. So it'd be closer to 143 than 142. That's rounding. If it's 5 and above, the drop digit, then we round up. If it's 4 and below, we leave it. as is. We don't round. Now, when we do calculations, it depends on the type of calculation we do. For addition and subtraction, we got to pay attention to the uncertain digit. The last digit is always the uncertain digit in science, so that depends on what instrument you're using. So this 5 is uncertain, that's the guess. The balance is guessing that because it's rounding it. This 0 is the uncertain digit here. We could have 0, this is significant. This 9 is uncertain here, this 2 is uncertain, and this 3 is uncertain. So that gives us uncertainty in this 8. You know, this 4 is certain, the 0 is certain, 6 is certain, 1 is certain. But this 5 screws everything up, and so that makes this uncertain. And what that's going to do is it's going to make these ones uncertain as well. And so what we're allowed is only one uncertain digit, so we have to drop 389 on the end here. And so it's a 3 we're dropping. If it's a 3 we're dropping, we leave it as an 8 here. And so this would be correct. So for addition and subtraction, we look at the number of decimal places. And so addition and subtraction, what we do is the answer, sig figs, equals the fewest number present. Actually, we don't call these sig figs. In addition and subtraction, let me get rid of the sig figs. You know, I don't even pay attention. Did I count any of the sig figs? I didn't count any of the sig figs. You know what I counted? I counted something called the decimal places. And so a weird thing happens. Here. How many sig figs is this? 4. How many sig figs is this? 3. So I have 3 sig figs here, but I end up with 4 sig figs in my answer. How is that possible? How that's possible is for addition and subtraction, we don't care about sig figs. We care about decimal places. And decimal places is how they line up. And that's going to dictate the uncertainty. However, for multiplication and division, we care about sig figs. So how many sig figs do I have here? 3. How many sig figs here in 1.436 grams? 4, and then 1.000 liters. How many sig figs there? You might think that's infinite, but it says here if the mass of 1.000 liters of gas is 1.436 grams, then it could have been exact, but in this case it wasn't. In this case they took 1.000 liters of gas and weighed it. And so there's uncertainty here in this volume, and there's uncertainty here in the mass. And so it turns out it's not infinite. The cases where it's exact would be things like this. In the cases where it's exact is in like density. Do you know what the density of gold is? Or iridium? I don't know. Do you know what the most dense element on the periodic table is? It's osmium, iridium. I think they're very close. And so it's either osmium or iridium. I think it's osmium, iridium. Those are the two. And do you know about how dense they are? About 20. So this is not being very precise. And so it's about 20 grams per cubic centimeter. Osmium is about 21, maybe 22. Iridium's the same, roughly. And which one wins? I forgot which one wins, but I should know. But anyway, the way we look at this is like this. How many sig figs in 20? It depends on how I write it. A zero following a non-zero may or may not be significant. And so if I wrote it like this, how many sig figs are there? If I wrote it like this, I would say that there's 1 sig fig. And that 1 sig fig means the uncertainty here is it's going to be between 15 and 24 grams. 15 and 24. If I put a decimal place in there, that changes the 0. So if I did 20 with a decimal point there, then that means that there are 2 sig figs here. So if there are 2 sig figs here, then that means this is between 19.5 and 20.4. And so it depends on the decimal. If I did 20.0, there'd be 3 sig figs. Well, this one I don't remember the exact density of gold. I'd say I know it to 1 or 2 sig figs. And so we'll leave it at this. Now this is going to be per 1 cubic centimeter. So how many sig figs are in 1 here? How many sig figs in 1? Well, you say 1 sig fig. And so that means it's anywhere between 0.5 and 1.4. Because I don't go to quite the same extreme that Bracolici does. But this is a density. In a density like this, we only want to keep the uncertainty in one component. And so we call this the density of gold. And so what we say is this is infinite. And what we say is in exactly 1 cubic centimeter of gold, there's approximately 20 grams. You can do that to 1 sig fig or 2 sig figs. And that way we throw all the uncertainty here. It wouldn't really make sense to say in approximately 1 cubic centimeter of gold, which varies from 0.5 to 1.4, this huge variation, there's approximately 20. You don't want to say approximately. You say in exactly 1 cubic centimeter, there's approximately 20. Now this one's different. The reason this one's different is because they tell you the mass and the volume separately. This is not the density. If they told us the density, then we put all the uncertainty in one term. So they measure the volume, they measure the mass here. And so it's a little bit different. And so the other example we did is this. In exactly 1 kilogram, there's approximately how many pounds? 2.202. So we wouldn't do this. We wouldn't say in approximately 1 kilogram. Approximately 1 kilogram would be 1 sig fig. So this would be varying from 0.5 to 1.4 kilograms. That's a huge variation, right? And so what we do is we say we hold one exact. So this is infinite sig figs. This would be 4 sig figs. And so that's the difference. However, this one I'm going to take is not infinite. I'm going to take this one as 4 because this was one of the measurements that they did. And each measurement contains uncertainty. You can't have an exact measurement. All right, so the rule for multiplication and division is you just take the fewest number. So here we have 3, 4, 4. So our final answer can't be this precise. Our final answer should reflect the uncertainty here. And the uncertainty here is 3 sig figs. So our final answer is going to be rounded to 3 sig figs. So we're going to have to drop the 8. If we drop the 828 here, we have to round the 2 up to a 3. So it comes out to 0.0823. And so this would be rounded to 3 sig figs. So multiplication and division, I keep track of the sig figs. Addition and subtraction, I keep track of the decimal places. We'll get more practice with those here. All right, for the ones that are definition, you have to memorize. And so this one you have to memorize. Now we have a definition for the mass. 1 pound is defined as 453.59237. But the problem with this one is there's too many sig figs. All we need for most of our calculations is how many? 4. So how would I round this to 4 sig figs? 1 pound is equivalent to 453.6 grams. So that's the one I had written up there earlier. So it's approximately 453.6 grams. That one you don't have to memorize because if we're going to memorize it, we should memorize the definition, but this is too long and too many numbers to memorize. For some people, they're easy to memorize the numbers, but for me, it's hard to memorize. And so this one would be given. The other thing also, 1 gallon, a lot of people say 1 gallon is 4 liters. Is that true or false? 1 gallon's 4 liters. I know 1 gallon's 4 quarts, but is 1 gallon 4 liters? That's true because 4 liters is only 1 sig fig. 1 sig fig means it could be anywhere from 3.5 to 4.4. And so it's true. 1 gallon is equivalent to 4 liters, but 1 sig fig has a lot of uncertainty. And therefore, we like to be more precise. So let me be more precise. 1 gallon is equal to 4.0 liters. True or false? That would be false. 1 gallon is not equal to 4.0 liters because 4.0 means it varies from 3.95 up to 4.04. And it's not in that range. 1 liter is exactly, not 1 liter, 1 gallon is exactly 3.7854, 11784 liters, exactly. But we're not going to memorize that. We're going to memorize this to you don't have to memorize this. You should, we're going to use this to 4 sig figs. If we use this to 4 sig figs, then 1 gallon is equivalent to 3.785 liters. So these two you don't have to memorize. This one you do have to memorize here. But like I said, we use it so much that it's easy to remember. This one I think everybody has memorized. Yes? How about this one? Yes? How about this one? Some people have this, some people don't. But 1 mile is exactly 5,280 feet by definition. How about this one? 1 pound is exactly 16 ounces. How about this one? 1 quart is exactly 32 fluid ounces. This one I don't have memorized. But I do have this one memorized. 1 gallon's 4 quarts. 1 quart is how many pints? 1 quart is exactly 2 pints. 1 pint is how many ounces? 16 ounces. So that one I have memorized. So I don't bother memorizing this one. But I do have 2 others memorized. And the 2 others is 1 quart is defined as 2 pints. And 1 pint is defined as 16 ounces. However, these ounces are not the same as these ounces, so we call these ounces fluid ounces. Fluid ounces is volume. A regular ounce is weight or mass. And so these ounces and these ounces are not the same. So in other words, 1 fluid ounce is not the same, is not equal to 1 ounce. It depends on the density. So let's say you had 16 fluid ounces of feathers versus 16 fluid ounces of gold. Are they going to weigh the same amount? No. The feathers are going to weigh a lot less than the gold. So we should know some of these definitions here. And if we know those definitions, we can do these conversions. So let's go from quarts to gallons to liters to milliliters. So if we start off with 1.0 quarts, how many sig figs is that? 2. And then we know 1 gallon is equivalent to 4 quarts. The quarts cancels as dimensional analysis, leaves us with gallon. How many sig figs is this? Infinite. Then we know in 1 gallon there are 3.785 liters. How many sig figs is this? 4. And so in exactly 1 gallon, there are 3.785 liters approximately, 4 sig figs. And then we can go liters to milliliters. How many sig figs is this? Infinite. And so our final answer should have 2 sig figs. This is wrong. Writing it to 2 sig figs, we can do it in 2 ways. Method 1 use scientific notation. So this would be 9.5 times 10 squared milliliters. Or we use the ambiguous 0. This would be 950 milliliters. So if we wrote this, this would be taken as 2 sig figs, versus if we wrote it like this, 950 with a decimal point milliliters, this would be taken as 3 sig figs. So this is 2 sig figs, this would be 3 sig figs here, by just incorporating the decimal point with the 0 at the end here. And so 2 sig figs, this is anywhere from 90 to 100 milliliters, in that range or something like that. Or no, that was too broad of a range. That would be 1 sig fig. This is 2 sig figs, so it'd be 94 and a half to 95. So 945 to 954 milliliters, a little bit narrower range. All right, we also do temperature measurement. SI unit of temperature is what? Celsius? The SI unit is actually Kelvin. So let's talk about the scales here by looking at the thermometers. And it depends on how 0 is defined. Do you know how 0 Kelvin's defined? 0 Kelvin's way down here, but the definition of 0 Kelvin is what? It's absolute 0, and that means there's no temperature. If there's no temperature, that means there's no kinetic energy. If there's no kinetic energy, it means that there's no motion. And if there's no motion, then everything's frozen. Nothing's moving, and it's the coldest we can get. We can't get lower. Is it possible to have lower than 0 kinetic energy? In other words, we have motion. Is it possible to have like anti-motion? Or negative? No, basically, you can't go any slower than 0. So 0 is the slowest you can go. And whether you're going forward or backwards is irrelevant, because motion is just motion. And so that's it. However, what does 0 degrees Celsius mean? Does 0 degrees Celsius mean there's no motion? No, at 0 degrees Celsius, there's still vibrational motion. Right, the molecules are vibrating. There's just no rotational. There's no translational motion. So 0 degrees Celsius is defined as the freezing point of water. So the freezing point of water is exactly 0 degrees Celsius, and 100 degrees C is exactly the boiling point. What is 0 degrees Fahrenheit? How is that defined? So 0 degrees Fahrenheit, I used to think that there was some scientist named Fahrenheit who walked outside the laboratory, and it was the coldest day that Fahrenheit had ever experienced, and thought, okay, since this is the coldest day, I'm going to call that 0 for the coldest temperature. But that's wrong. Do you know how 0 degrees Fahrenheit was defined? It's like when you make ice cream. Have you ever made ice cream? When you make ice cream, you want to cool the mixture down. And you could use ice to cool it down, but ice is going to cool it down to what temperature? Well, it depends on how cold the ice is, because you can get ice really cold. And so let's say you have some really cold ice and you want to cool it down. But the problem is there's not good heat conduction between solid. It's like if you jump in snow versus jump in ice water. You'll get cold a lot faster jumping into ice water, because there's good thermal heat conduction, that is heat transport between you and the water. And so in other words, when you make ice cream, you want the water to stay liquid to colder temperatures than 0. So the way that people do that is they dissolve salt in water. If you dissolve salt in water, what it does is it pushes down the freezing point so it stays liquid at lower and lower temperatures. And then getting into an ice bath versus getting into an ice water bath, there's a huge difference. If you jump in a bath full of ice cubes, you aren't going to get so cold so quick. But if you jump into a bath of ice water, your temperature is going to drop rapidly. And that's just due to heat transport. And so 0 degrees Fahrenheit is defined as this. Fahrenheit made a saturated salt. That is, he dumped as much salt as would dissolve and then froze it. And that's the temperature at which it freezes at. And so it's the freezing point of a brine solution. That's 0. But anyway, at 32 degrees Fahrenheit, that's exactly the same as 0 degrees Celsius. And at 212 degrees Fahrenheit, that's exactly the same as 100 degrees Celsius. It turns out there's no uncertainty there. They're exactly the same. And then for Kelvin, we have this. And so what we're going to do here is we're going to do a little bit of scientific method. The scientific method begins with observation. And so my observation is this. At 0 degrees Celsius, what's the Fahrenheit temperature? 32. And this is exact. There's no uncertainty there. And at 100 degrees Celsius, what is the Fahrenheit temperature? 212. And this is also exact. And so we take our observation first, and then what do we do? Following observations. We look for patterns. And in science, the way we look for patterns usually with numbers is we try graphing things and seeing if there's some kind of pattern in the graph. And so on the y-axis, I'm going to plot the temperature in degrees Fahrenheit. On the x-axis, I'm going to plot the temperature in degrees C. So when I'm at 0 degrees Celsius, I'm at what temperature in Fahrenheit? I'm at 32 degrees Fahrenheit. And if I'm at 100 degrees Celsius, what is my Fahrenheit temperature? 212. So we'll go ahead and do that. This will be 212 degrees Fahrenheit. And then I'm going to plot another point here. And then I look at the relationship, and the relationship turns out that it's linear. Linear means it's a straight line relationship. So if I do some more temperatures, here I'll see a straight line. So I need one more temperature to make sure it's not curved and that it's linear, but it's linear. If I have a linear pattern like this, then the most concise way to define this pattern is mathematically. So what I'm going to do is I'm going to reduce this graph into a mathematical equation. Do you know what the equation is going to look like? It's going to look like y equals mx plus b. And so what is y? Y is the temperature in Fahrenheit. What is m? M is the slope, so that's delta y. What is my delta y here? So it's 212 minus 32. 180 degrees Fahrenheit, divided by my delta x. My delta x is 100 minus 0, which is going to be 100 degrees Celsius, times the temperature in degrees Celsius, plus the intercept. What's the intercept? 32 degrees Fahrenheit. And so what a lot of people do is they simplify this equation, and so we're going to simplify it. The simplified version of this equation is the temperature in degrees Fahrenheit is equal to 180 over 100, which reduces to 9/5, times the temperature of degrees C plus 32 degrees. And so we would call this a what? If we have a mathematical pattern like this that's reproducible, then we call it a empirical law. And so this would be the law of temperature. Nobody calls it a law. People just call it the temperature relationship. And we can rearrange this, so we can derive the equation for degree C. Degree C is equal to degrees Fahrenheit minus 32 degrees times 5/9. Now, we don't have to come up with a hypothesis. We don't have to come up with a theory. We can just use the law. And in fact, that's all we do. We just use the law to convert what we call ambient temperature. For ambient temperature. Ambient means like room temperature. What is the room temperature? Or the temperature of whatever we're studying. We have another thing we do, and that's for delta T. Do you know what we use the symbol delta for? Change in temperature. So here we're using a different method. This is algebraic. We have an algebraic equation. This is not dimensional analysis. For delta T, we use dimensional analysis. And that is, let's go back to this, 180 degrees C for every 100 degrees Fahrenheit, which means that there's 1.8 degrees Celsius for every 1 degree Fahrenheit. So let's say the temperature increased by 1 degree Fahrenheit, the room temperature. If the room temperature increased by 1 degree Fahrenheit, how much did the Celsius temperature increase by? 1.8 degrees. And so in other words, a Fahrenheit is a little bit bigger than a Celsius. We can see that here. If we look at this thermometers again. So, although this is hard to see, well, it might be easier to see off this one. For every 100 degrees C temperature increase, how much did the Fahrenheit temperature increase? So if the Celsius temperature increased from 0 to 100, that's 100 degrees C temperature increase. How much did the Fahrenheit temperature increase by? 180, because going from 0 degrees to 100 degrees is equivalent to going from 32 to 180. You see that? And so that would be a temperature change. And so here, that would mean we would use dimensional analysis for that. And so if I had a delta T of 100 degrees C, delta T, then I know that that there's 1 degree Fahrenheit for every 1.8 degrees, 1 degree Celsius. I have this backwards. Let me redo that. There's 1 degree Fahrenheit for every 1.8 degrees Celsius. So the degrees, actually, no, I have this backwards. 1.8 degrees Fahrenheit, sorry, for every 1 degree Celsius. That's what I meant to say. Which is going to give me 180. This is a temperature change. So this has to be labeled delta T versus ambient. ambient temperature is this. Degrees Fahrenheit is equal to 9/5 degrees C plus 32 degrees here. So if I'm at 100 degrees Celsius ambient temperature, what is my Fahrenheit? So that's going to be 9/5 times 100 degrees plus 32. And so this is going to be 1.8, 180. This is going to give me 212 degrees Fahrenheit. So I could have a temperature change of 100 degrees C. That's going to be a temperature change of 180 degrees Fahrenheit versus an ambient temperature of 100 degrees C, which is going to give me an ambient temperature of 212 degrees Fahrenheit. So we have to use two different equations depending on the calculation. If it's a temperature change, we use dimensional analysis. If it's an ambient temperature, we use algebra. The reason we have to use algebra here is because the zeros are offset. In all the other ones, you know, for example, if I have 0 grams, how many milligrams do I have? If I have 0 grams, how many milligrams do I have? 0. And so the two zeros coincide. 0 milligrams means 0 grams. 0 grams means 0 milligrams. However, if I have 0 degrees Celsius, do I have 0 degrees Fahrenheit? No, they're offset. They're offset by 32, so I have to add the correction factor of 32 at the end. So I do a dimensional analysis, plus or minus 32, depending on how I'm going to correct it. And so that's the difference there. And so this is why we have to do this. Now for Kelvin, it's pretty straightforward as well. Celsius and Kelvin. So let's go ahead and do this one more time. Okay, let's take our observations. Our observations on degrees C and Kelvin. If I have 0 degrees C, do you know what the Kelvin is? 273. It's actually 273.15, but I'll just do 273. If I have 100 degrees C, it's 373 Kelvin. This is probably precise enough. And then I'm going to graph this. Maybe I'll put Kelvin here and degrees C here. And so 0, let's go to 273. Oops. 0 here. We'll go to 273 here. Sorry, not here. And 100, we'll go to 373. Here. All right, this is also linear, which is going to be defined by y equals mx plus b. Y is Kelvin. M is delta y. So 373 minus 273 is 100 Kelvin. Delta x, 100 minus 0 is 100 degrees C, times degrees C plus the intercept. What's the intercept? 273. So I'm going to simplify this. The Kelvin temperature is equal to the degrees C temperature plus 273. And so this is the law of Kelvin and Celsius. And then I can rearrange this to calculate degrees C. Degrees C is equal to Kelvin minus 273. So a lot of people memorize this, but these are easy to derive. These would just come from. And we're perfectly fine with laws. Laws aren't a problem here. All right, so there's some temperature conversion problems. So if we want to go from Fahrenheit to Kelvin, what we do is go from Fahrenheit to Celsius, Celsius to Kelvin. Or if we want to go from Kelvin to Fahrenheit, then we do it in 2 steps as well. The same thing, this is for ambient. But for delta T, we use the relationship here. This is the conversion factor for delta T. And so for delta T, 1 Kelvin is equivalent to 1 degree C. So if I had a 10 degree C temperature change, what was my delta T in Kelvin? It would be 10 Kelvin. that would be the delta T. So if the Celsius temperature increased by 10 degrees C, the Kelvin temperature increased by 10 Kelvin. However, is 10 degrees C ambient temperature the same as 10 Kelvin? No, 10 degrees C is awfully cold, but 10 Kelvin is almost at absolute zero. And so they aren't the same ambient temperature, but as far as delta T goes, they would be the same. And so the same thing happens here. This is dimensional analysis for delta T. We use a different equation. And for ambient, we use the algebra equations here. And so the conversion factor, this would be the conversion, 100 over 100. That's our conversion factor. And so this is the only confusing thing for the temperature, and this is because of the way the temperature is. All right, are we good with that? So we have another 20 minutes, so we're going to have another quiz here. But this quiz is a bit long. This quiz is 8 problems from your supplement. Can you do this, because this is 8 problems, can you do this on notebook paper? If you don't have any notebook paper, then I have some here you can use.